Khurram, thanks very much. Thank you.
Hi, everyone. My name is Aisha, and you might know him. He's Khurram. So we are going to share a talk. But before going to the talk, I want to just do a bit of the introduction about me. I'm a teaching specialist at a School of Mathematics and Statistics in the University of Melbourne. Right? You all know about the topic, so I'll dive into it later on. But I want to let you know why I'm here and how you're going to get what's the use of my talk. So I want to start it how do you make your student to come back again and again in your classes, right? I want to start with this thought. I would like you to think, how do you want your student to come back in your classes again and again? You don't want them to get fail and come back again and again, of course not. So what I meant to say, let's say if I'm doing Cal 1, right? I want them to come back in Cal 2, right? And they can only come back in the new course when they are satisfied with my teaching, right? So today's talk, is about, that motivational example of a first year mathematics, right? So when the students, they come in the classes, like in Cal 1, Cal 2, linear algebra, so they have this type of question. Why do I have to study Cal 1, Cal 2, linear algebra? And then, is it not enough mathematics that we already learned for our major? And what are the applications of Cal 1 and Cal 2, right? So I think it is the responsibility of all of us to give them the real world application, to connect their teaching with the real world, right? So I'm going to start the talk with some analogy, okay? So later on, I'll go into the examples. So you can see, I have a tourist here. He's planning to go to K2, right? And another tourist, he's planning to go to the Blue Mosque, Hagia Sophia, which is in Turkey. And later on, he wants to go to Egypt Pyramid, which is in Giza, right? What's my role in here? You can see a backpack. So I'm like a mentor for them. I'm going to ask these two tourists to put all the important ingredients to make their journey successful, right? So it could be passport, like a mobile phone nowadays, and the charger. Money, we don't use money, we use cards, and etc. everything, right? So if they're going to listen to my advice, so it will make their journey successful and safe, right? So we all are mathematicians. So what does mathematician wants? How we see the world around us. So we have so many natural phenomena and physical phenomena. So I'm going to just let you know how to motivate students, and we can give them examples in the real world. So let's say if we are looking at the moon, okay? So we can say, okay, if it's circular, so we can express it in terms of this equation, the well-known equation. Say it's a sphere, so it could be the equation, right? So another natural phenomenon you can see here, a planet is revolving around a sun and is creating a trajectory which looks like ellipse to me, right? So I can explain to the student this natural phenomena, right? And I can express it in this equation, the well-known equation, okay? So now I'll discuss about some physical phenomena, how we can get the interest of the students in the subject. Because as I mentioned in the beginning, they don't know. And I want to add one little story I forgot in the beginning. So I want to add here. Last semester, I was doing Cal 2. So a student, she came to me, her major was computer science. She came to me, she was saying, Miss, I don't know why I'm studying mathematics. I hate mathematics. And I can do all the coding without mathematics. Then I smiled, I said, really, do you think so? She said, yes. I don't know what's the use of mathematics in computer science. Then I told her, do you know what is going on in the background? In the background, we are using coding, algorithm. This is all mathematics. So she was really surprised. And she was very happy because she didn't know that. Anyways, let's come back to the physical phenomena. So these are the examples the students they usually learn in VCE and Calvin Cal2. The first example, you can see a physical phenomena equation of a simple harmonic oscillator. So the spring is keep going on and on because there's no external force which is stopping it. And this is the differential equation, right? In the second example, you can see a physical phenomena equation of a damn oscillator. Let's say it has some maybe internal force, maybe external force, which is stopping it. So you can see, yeah, particle is going from high altitude and trying to reach to zero, right? So this is a very useful example. We'll learn it. And then the third one, you can see a boy is throwing a ball, which is creating a projectile motion. So we can express it in this equation, right? So it's very interesting. Okay, so now I'm going to give you some bit of the advanced example. I'm going to create a scenario here. So let's say scientists, they are tracking an asteroid. You can see, I need to use this one. This, I don't know whether you can see this thing, right? This is an asteroid. It's forming a trajectory. Okay, so scientists, they are very interested to know where it's going. It might be hitting to the sun. It might be hitting to Earth. It might be hitting to some planet, right? So they have this numeric data. At Theta, maybe it's covering a displacement at x naught, etc., etc. Unfortunately, they don't have any function. So what they're going to do? They are going to plot the data. Why? Because they need to find the trajectory or the equation. Okay, so how they're going to find the equation, a function? They can use interpolation techniques and might be using least square shooting, Newton's forward backward interpolation, Lagrangian interpolation, cubic splines, etc. Okay, and once they find the function, they can differentiate it, they can find the velocity. And then they again differentiate it, they can find the acceleration. So the crunch idea is that basically everything is depending on the like Kelvin Kelch, right? If they do differentiation, they could able to find velocity and then acceleration, right? Like as I mentioned, it is beyond first year, but it's depending on the basic mathematics, right? For first year students. Okay, here, let's say we are converting discontinuous periodic signals to continuous. And if we are talking about the heartbeat, all right? So in the first picture, you can see there's something not right with this heartbeat. It is irregular heart rhythm, okay? In mathematical terminology, we can say it is discontinuous. And in the second picture, you can say it's continuous and periodic, all right? So we have very advanced technology, and nowadays doctors, they are using pacemaker device. What does it do? It regulates an irregular heartbeat. Okay. So why I'm giving you this example, I'm letting you know in the making of pacemaker, we are using advanced mathematics, signal processing, control theory, and Fourier. So I'm going to let you know how it's going to connect with the first year mathematics. Okay. So here, if you see, we have signals, the blue one, they are discontinuous, but periodic. And we are approximating, you can see the red one, with the help of Fourier series to make them continuous. Okay. Is mathematics helpful to deal with it? Yes, of course. All right. So let's say we have taken a square wave here. Okay. You can see, okay, there's a discontinuity at the bottom of it. And I've taken an infinite series. You all know Fourier series is an infinite expansion, right? So the more terms you take, the more accurate and precise result it will give you. So in the second image, you can see we have taken 5 terms. It is continuous but not very precise. And then we have taken 10 terms and then 20 terms. So it will give you more precise and accurate result. All right. Okay. So it's all, you will say, okay, it's beyond first year mathematics. But if a student did know integration, they were able to do 4 year, right? They might be doing differentiation if they are doing by parts, right? Okay. So yeah, so my part of talk is gonna finish here. I hope you've enjoyed my talk and you have learned something so you can implement in your future studies. All right, thank you so much for your time. And I'm gonna request Dr. Khurram Kamran, so he's gonna continue talk from here. Thank you.
Hello everyone, my name is Khurram Kamran, and I'm the teaching specialist at School of Mathematics and Statistics, University of Melbourne. I'm just trying to continue here the talk what Aisha was giving here. Before I start, actually, the main thing is that I think a couple of years ago, I had some of the students from the arts, and they were trying to make something like the logo. They got the assignment, and they wanted to create some logo with mathematical expressions. So they were saying that is there any way to express something like the flower or something on our computer or mathematical equations, right? So at that moment, I use this expression. You might be familiar with this polar sketching, right? R is equal to a plus beta 1 minus cos k theta. And this k is actually represents the number of petals in our this flower sketch, right? So maybe I think I can able to show you some of the animation here. So that's the first animation I just tried to do. And student actually really liked that one. And they were motivated that there are too much mathematics because this polar curve is actually not the part of their course most of the time. But actually they were very amazed with this application that we have some of the things that we can present in mathematics being an art students, right? And they use actually that one to create the logos, right? Okay, so this is another example that Aisha was giving, and it is another example that we can engage our students by giving some of the examples so that they have a motivations to look forward, to engage in their subjects, right? Let's go. Okay, so our next example in our application point of view, the real world, the dish antenna. Right. So actually, what is the dish antenna? Dish antenna is actually is trying to get these signals from the space, and that's the parabolic reflector here. And we have a beauty of our parabola here. You might be familiar with that one, that if these rays are coming towards this parabola, so they can reflect from it and converge it to a single point. And that single point is referred as the focus of our parabola, right? So more interesting thing here is that this point here in this dish is referred as the LNB, right? This is the point where we usually put the focus. So this is our parabolic reflector, and its focus is somewhere here. Definitely, if we are familiar that what is a parabola, how to find the focus of that parabola, definitely we could able to find this position, which is called the LNB. The most interesting part is that this actually LNB, usually in our buildings, in our homes, we use that one, and they are connected through the cable, and it goes towards our inside the home and connected with a particular device, what we call receiver. And then from receiver, we connect our television, right? So in that situation, actually the receiver, what the receiver is doing, receiver is receiving all these signals. These signals could be discontinuous here, right? But what is the purpose of the receiver? Receiver is going to collect all those signals and convert those signals to a continuous signals, right? That's why whenever we see our pictures on our television, even in the live programs, there is no distortion in that one, right? And what is the thing behind it on that receiver? So the flow of current in that receiver is through the Fourier series because these are all signals and then they may be discontinuous because the frequency is constant for every particular signals what you are receiving. So that's why we can construct easily the Fourier series what Aisha mentioned earlier, right? So that is the main purpose of this applications to show you that this is more, definitely there are many things for the electronic engineering students they might be using to construct their circuits for these receivers, right? I think you might be familiar with all those parabolic kind of stuff, right? And this is the focus and that's the lattice rectum. So that's the point where we have to converge all the rays from our parabolic reflector in the dish antenna. So this is one of the example what could motivate our electronic students who are studying electric or electronic engineering. Okay, another problem here, the networking problem. For example, we have these 4 buildings, and maybe if you are a manager and you would like to provide the internet facility to these buildings, and you have the server located over here, right? So definitely being a manager, you have to make the cost of that one is cost effective, right? So you need to minimize that distance, right? So to make this thing as a mathematical modeling, so one thing observe here from the top, so we have to connect our points over here in the building over the top here, over here, over here, and over here, anywhere around the building's top, right? So if you look from the top, it would look like this kind of a structure. There are 3 buildings. The tops are look like square. Another one is the top one is from a circular region. And that is the server, which is located somewhere here. Let's say this is at 02, right? So what we need to do being a manager, you have to minimize that cost. It's not only the cost. If you have a very minimum displacement from the building from this server, definitely you will have a good access to the data, right? You have a fast working network. That's what you refer to. Okay. So in that situation, this point could be anywhere on that building, but around the building corners, right? The same thing here. So we referred here this X1, Y1. Here for building 2, this is X2, Y2. This is X3, Y3, and that is X4, Y4. Right? And definitely all of you are familiar that how to find these distance from here, D1, D2. So these are the distances. So we have to minimize all that distances, right? Minimize that. But there are some subjected conditions because there are some limitations here. So you can see that if let's say this is your X1, Y1, it could be anywhere around the building, right? But X1 cannot exceed from, sorry, could be greater than 2, but not exceeding from 4. So this is one of the conditions what we can impose on X1. The same thing, you cannot go beyond this building. So this Y1 should be between 0 and 1. That's what we have imposed here. But the same thing we can impose for this building, and over here, because we cannot go inside the building, or maybe we can go, it's up to the building construction, definitely. So the radius, let's say the radius is 1 unit here. So the radius remains less than equal to 1, right? So these are the constraints. So being a network manager, you can able to optimize this problem through your mathematics. And definitely this optimization is a little bit upper level mathematics from the first year, but definitely you need what calculus 1, calculus 2, and linear algebra knowledge, right? To tackle these kind of things. So definitely if you are not good enough in your calculus 1, calculus 2, and maybe linear algebra, so it's hard for you to tackle the problems like that, right? Again, I guess most of you have been teaching this traffic flow linear algebra. So they are familiar with this traffic flow system. So these are the streets, and definitely these are the corners of the streets, and these are the flow of the traffic along that one. And these equations can be produced through the flow in and flow out at the particular corner here, A, B, and C, or nodes, you might say. So these are the most familiar example what we usually use in linear algebra to demonstrate some application of linear algebra, right? So this is a very good example, but if we show some advanced mathematical modeling, that's what helpful for them. For example, because nowadays in first year level, there are too many students from different disciplines, and it's very hard to show a particular example for a particular student's course, right? For example, if I'm interested to show this one, it could be possible that might be interested for engineering students, right? But might not be interested for arts students, might not be interested for maybe some medical students, could be possible, because that's relevant with the traffic flow. So they might not relate together these things, right? Maybe for the business students, they might not interested in that one as well. So that's why they disengage, right? So we have to give the example according to the requirement of the students. If definitely if we give the example, a particular example, which is in the interest of the student, then definitely what would happen? It impacts on their studies, right? They try to engage, they will take the interest and just keep going in their subjects. Okay. So here's an advanced, little bit advanced transportation model, what I'm trying to discuss here. Maybe you might be familiar because you have been teaching mathematics for a long time, definitely. So this is a transportation model where we have been, for example, if you are a manager of a company and you have these warehouses here and you have a distributor here, right? And you would like to manage that to supply, because they may have to supply something here. For example, the cars, it could be possible some other commodities, right? So if they have to transfer the commodity from, these are the warehouses and these are the supplies of these ones, right? And these are the destination, this X, Y, and Z. And these are the demands of our distributors, right? So what are these numbers here? So the numbers actually represents that if you have the warehouse A, and if you are transfer the commodity of whatever the requirement you have in this problem is going towards destination X, so the transportation cost is going to be what, 3 units, right? So it's mean that if you are sending one, let's say if you are sending one truck from A to X, so its cost is going to be 3 units. Could be anything, $300, maybe something, I don't know. But these are just the numbers here. From B to Z, it indicates that you cannot transport anything from B to Z. That's the meaning of this dash here. Again, we can represent this system as a networking problem. Yeah. And in that networking problem, here we have A, B, and C. These are the capacity of these warehouses, right? We had 3, right? And we have 3 destinations here. So these lines actually represents the transportation cost for every particular destination from the given warehouse. So to tackle these kind of transportation problem, we usually have this supply and the demand should be same for both of them. But unfortunately, this demand is higher, right? And this supply is lower. Yeah, because demand means that your distributor wants more supply from you, so it can increase anytime, right? But you have a certain capacity, so you cannot exceed your transportation from that particular capacity, right? So that's the supply. Okay. To tackle these kind of model, we actually need to balance the transportation model. So here we have 4, and we have so introducing the sum of that demand should equal to the sum of this supply. And because the supply is smaller than this demand, that's why we are introducing one of the dummy warehouse here. And the cost associated with that one is actually 0, right? So now if you sum them and you sum them together, so that's going to be actually the balanced transportation problem, right? So we don't know exactly how much we have to ship from A to X. So let's say if from A to X, the transportation is going to be XAX, the same thing XAY, from A to Y, and from A to Z is going to be XAZ. So these are the variables what we can introduce to define the mathematical modeling for that system, right? So this is the total cost associated with this transportation. So 3 times of XAX, which is here, 2 times XAY, which is here. And then we are summing all these costs. Definitely the contribution of these one is actually 0 because this is the dummy place, right? So there is no cost associated with that one. So these are the supply constraints. So at any instant of time, if you are sending anything from here or here or here, so definitely the total sum should not exceed the 200 units, right? The same thing you can implement on B and C. So these are all the maximum supply what we have. So these are the inequalities actually here. And we refer these are the supply constraint. And that one is our demand constraint because whatever we are receiving from here, the quantity, that should equal to 250, exactly the demand, or maybe exceeding from the demand, greater than equal to 250. For the timing, we are using equal to sign here, right? So in that situation, we have a mathematical model for this transportation model, right? So being a manager, you have to minimize that cost subjected to these conditions. So someone might think that these are all inequalities, right? But in mathematics, usually we can convert these inequalities by introducing new variables into a new system of linear equations. And when the linear system exceeds from 3 or 4 variables and more, then definitely, because we are just using 3 warehouses here or 4 warehouses. So if you go beyond from that one, definitely you need to know that how to solve that system for the system of linear equations, right? And definitely you might have to use the computer as well, computer softwares to solve that large system. Okay, so this is one of the motivating example for our first year students who are maybe studying in economics or maybe in business, right? Again, this is another interesting thing because usually the students in computer science, they don't know that how our particular softwares actually works because they usually, what they usually use these softwares. They don't know exactly what's going on behind these softwares, right? However, we know very well that everything behind any computer software, all the mathematics is behind it, right? And definitely our students not willing to see all those things, right? So that's why they're just using the softwares. So I'm just giving a simple example here as a smiley face here. So you might be familiar with these translation of x is equation, x is equal to x plus h and y equal to y plus k. So these are usually the things what we use in linear algebra, right? How I have created that one, definitely you can imagine I might have used some circle equation, right, to produce all those things. But would we able to use translation of x's to animate that one? So let's see one of the picture here, animated one. Again, that's all what a mathematics behind it. I'm not using any sophisticated software here. This is just exactly simple mathematical equations and equation of a circle. That's it, nothing else, right? So it's been that if we motivate our students by these kind of examples, hopefully that they would able to learn more things and they are curious about actually what they have to take from our subject, right? And I'm just about to finish my talk here. Okay. So what is the conclusion here? So definitely you might have seen that with these examples that our mathematics actually is serving everywhere in every discipline, no matter it's arts, no matter it's business, no matter it's engineering, social science, everywhere, right? So some of the people, they say that mathematics is the queen of all sciences, right? But one of my professor, he was from France, and he used to say that mathematics is the most obedient servant in every discipline, right? Most obedient servant, because he serves everywhere. But okay, and definitely student needs motivational example to engage in their discipline. So if we are able to provide some of the motivational examples to engage them, definitely they are curious and they will learn more deeply. That is similar kind of thing. I agree with Paul. This is sort of storytelling, right? From the very beginning, we have to tell something that what we are looking for. If we give these kind of stories, actually, they'll learn more. But this is another way, animate, or maybe using our mathematics to show their story, right? Okay, so maybe I'm not sure that what time is the best time for you to introduce all those kind of things, but the best time is the week 1, or maybe in week 0, where you can show some, maybe if you create some video for these kind of problems, and then you can share with the students, they might get motivated with that one, right? Okay. Thank you very much, everyone. It's time for the acknowledgement for our MSLC manager, Dr. Anthony, and our head of school, Professor Dr. Burnham, and our family.